the graphs of sine and cosine functions, we're going to use a technique that we've used in the past. We're going to begin with kind of a degenerate form of both of those functions and look at their graphs and then kind of add coefficients here or there to see how the behavior of the graph will change. And fundamentally, we're going to take a point plotting approach to graphing. Well, consider f of x equals sine x, and the working model, the model for graphing is y equals sine x, as we've seen in the past. Now, we can think of the x here as either a real number, or an angle measured in radians, or an angle measured in degrees, and we get the same result in all of this study. Using the point plotting method, we just fill in a table of values. Now, I've allowed x to take on values 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm thinking in terms of real numbers here, but if we wanted to, we could say 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, and again, have the same result. Okay, so plugging in here, either using the calculator or studying this using the unit circle or using right triangles, we find that when x is 0, sine x, which is y, is 0. And when x is pi over 2, the sine of pi over 2 is 1. And when x is pi, the sine of pi is 0, and so on. Okay, let's plot the points. Now, in structuring the coordinate plane for graphing, we need an axis that well, the x-axis is an axis for either the real number or the angle measured in radians or the angle measured in degrees, you see. And so it really follows the same idea that we have had all along with graphing. Now, one cycle of the graph will occur in an interval that is 2 pi in length. And so I'm identifying the position of 2 pi here, and I'm identifying the position of 4 pi. And now we need some significant values in between these two. Now, right in between 2 pi is pi. Right in between 0 and pi is pi over 2. And in between pi and 2 pi is 1.5 pi, or 3 pi over 2. Now let's plot points. I'm just going to look over here and plot the points. And you just stay right here and watch how this graph is going to behave. 0 goes to 0. Pi over 2 goes to 1. And then at pi, the graph comes back to 0. And then at 3 pi over 2, the graph drops down to -1. And then at 2 pi, it comes back up to 0. And then the whole cycle starts over again. And the graph kind of looks like the graph of a polynomial function in that it's a continuous graph and it's just kind of curvy. It goes like this. You see, that's one complete cycle. Now, that complete cycle for a graph of sine or cosine is called the period of the graph. And this distance above the x-axis or below is called the amplitude. And so the amplitude for this graph is 1. You see, and that distance is 1. This distance is 1. Okay, so amplitude and period. Now, the graph continues on forevermore in both directions here, because we're talking about all real numbers as replacements for x. Now, in some circumstances, we will want to limit the domain here of our functions, but for all practical purposes, we have to assume that we're going forevermore in both directions. So we go out this way, we go down to the bottom of the amplitude over here at a negative pi over 2, you see, and continue just the process this way. In the other direction, well, let's see, in between 2 pi and 4 pi would be 3 pi. But the idea is that if we have these little intervals, you see, of the important points for the graph, then we can just go from interval to interval and understand what's going on. That from here, we go to the top of the amplitude, you see, at the next important point. And then we come back to the x-axis for an x-intercept, and then to the bottom of the amplitude for the next point, and then back to an intercept. So the graph then goes like this. Now, in a similar way, we can analyze the graph of the cosine function. We just think f of x is cosine x, or y equals cosine x, and now we make a table of values. Now, the table begins the same way. We're utilizing these important points for x, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And now we fill in for y. And again, we can fill in a lot of different ways. But we find the cosine of 0 to be 1, the cosine of pi over 2 to be 0, the cosine of pi to be negative 1, the cosine of 3 pi over 2 to be 0, and then 1 once again. And these values for y look roughly familiar to the values for y on the sine curve. And in fact, the curves look pretty much the same, except they're just kind of shifted a little bit on the coordinate plane. Let's have a look. 0 goes to 1. So when x is 0, y is 1. And when x is pi over 2, y is 0. And when x is pi, we go to the bottom of the amplitude to negative 1. And then when x is 3 pi over 2, we go back to the intercept. And then when x is 2 pi, we go to the top of the amplitude. So for the cosine curve, we're starting at the top of the amplitude. We go through the x-axis. We go to the bottom of the amplitude, and then back through, and then to the top again. So this is the fundamental cosine curve. And then it obviously continues in both directions, just like the sine curve did. So from the top of the amplitude, we go back to an intercept, then the bottom of the amplitude, intercept, top of the amplitude. So here's how it looks. And here's how it looks over 2 periods. You see, we're graphing 2 periods of this function. Consider y equals 3 times sine x. Now, to construct the graph of this equation, we'll kind of go from the graphs that we talked about before, the basic sine graph. And the way to do that using a point plotting method is like this. Make your table of values so that you have 3 columns in the table. An x column, a sine x column, and then it's pretty easy to calculate a column which is 3 sine x, which is y here, which is the y values here that we're calculating. So for the x sine x, you see those are the columns that we've had before. When x takes on these values, sine x takes on these values. So 3 sine x means 3 times all of these rascals. So 3 times 0, 0, 3 times 1, 3, 3 times 0, 0, 3 times negative 1 is negative 3, 3 times 0, 0. Now, remember that y is 3 sine x, so this is y, and this is our xy pair, then, that we're plotting to see the graph. Okay, so away we go. Now, in structuring the coordinate plane for graphing, we just make a vertical plane, and now I'm identifying 3 and negative 3, and we'll see why in just a minute. But on the horizontal axis, I'm thinking about 0 to 2 pi, 1 complete cycle, you see, and then just subdivide this little interval into 2 parts, and then subdivide that into a couple of parts. You see, just take half, and then half of those halves. And now this is pi and pi over 2. And very quickly, we can sketch the graph. This is 3 pi over 2. Okay, now we just plot a bunch of points. 0 goes to 0, and then pi over 2 goes to 3. Pi goes to 0. 3 pi over 2 goes to negative 3. And then 2 pi goes back to 0. And the cycle continues in both directions. So the graph then looks like this. And we're seeing that when we tack on a coefficient, that just as we may have suspected, come back over here with this, that y equals sine x has a particular kind of pattern, a particular behavior for the graph. Now, these are vertical distances associated with sine x. Right? Now we're talking about 3 times those vertical distances. You see, so no wonder the graph tends to stretch this way. For every vertical distance that we had in the sine curve, we are thinking about 3 times those vertical distances for the curve associated with this equation. So it turns out that when we have a coefficient, it will cause the graph to be either elongated or maybe squashed a little bit like this. You see, what if A were, instead of 3, 3 causes it to stretch this way, what if it were 1/2? So then 1/2 would be half as high as the original graph that we looked at earlier. And by the way, this is where 1 is on this particular graph. I have changed the interval distance for my vertical axis. So the graph here looks pretty much like the one that did before, but notice that 1 is right here. So the graph of sine x for this coordinate plane would just go up to right here and then down to right there, you see? And so that it's really stretched up here to 3. But at any rate, it's the idea that that coefficient will cause a stretching or a compression of the graph. Now, if the a value is negative, think about what that would do. You see, if that a coefficient were negative, that means we would have the negative of some vertical distances that were associated with the regular sine curve. The negative of vertical distances, well, that's our concept from before of flipping the graph over. So if we were talking about an a value, and let me just talk about a pretty simple one. What about y equals the negative of sine x? You see, just the negative of sine x. Well, all that would do is take the regular sine curve, which is like this. You see, that's the sine. Here's 1, and there's 1. So the amplitude here is just the 1. Okay, and it would just flip it over. So the graph of that rascal would be, well, think about flipping it over, and it would look like this. Now, I'm going to make it dotted here just for emphasis, but it would look something like that. So the a, that coefficient that appears here, the a that appeared over there, will tell us whether or not the graph is kind of flipped this way. If it's negative, it'll do this. And if it's positive, then it will stretch or compress. Now, it'll stretch if the number is larger than 1 or smaller than negative 1. It'll kind of appear stretched like this. It'll sort of look compressed if that number is between negative 1 and 1.